Okay, the Bragg's law we have seen. Okay, the same thing, see the animation. The waves are incident on here and it is scattered. The waves are scattered here based on the glancing angle. If the angle is changing, then here the path difference is also changing. So based on the path, the ending lines are also changing. Here see, the angles are changing here. If this glancing angle change, this path difference is also changing. That means if you change the angle theta, then obviously it is changing the angles. That is what the Bragg's law. That means 2D sin theta is equal to n lambda. If the theta, if you are varying theta, then it is whether it is coming n lambda to n plus lambda is changing. So this is what Bragg's law in this course. And now just I want to do some exercise. Okay, so now we are going to do some numericals on Bragg's law. So here the numerical is when a beam of X-rays of wavelength 18 angstrom unit is incident on a crystal surface, the second order maximum is obtained at a glancing angle of 15 degree. Calculate corresponding interplanar spacing. This is what is given. That means based on the Bragg's law, the radiation is incident on a crystal planes, then at a fixed angle, then second order maxima is obtained. That means diffraction is taking place. Then we have to find interplanar spacing, means this spacing we have to find. So let us start this one. Okay, let us solve this problem. Okay, let us solve this problem. Solution. First, what is given? Just we have to identify. What is given? Lambda is given. It is 18 angstrom units. Then it is second order maximum. That means n is given. N is second order 2. And glancing angle. That means theta is given. Theta is 15 degree. What you have to find? Interplanar spacing. That means D you have to find, or we have to find. That means what is the formula? 2D sin theta is equal to n lambda. This is the formula. Now what you have to need? D. So D is equal to n lambda by 2 sin theta. Then n is what? How much? 2. Lambda means 18 angstrom units by 2 sin theta is how much? Theta is 15 degree. That means 2 will get cancelled. 18 by sin 15. Then if you solve this one, you will end up with 6.95 angstrom unit. That means the interplanar spacing of this particular plane, if 18 angstrom unit X-rays are incidented at 15 degree angle. So this is the answer of the interplanar spacing of a given problem. Okay, next problem. If you say next numerical, okay, next numerical. Let us read this one. What is given? Calculate glancing angle on the cube 100 of a rock salt crystal. Lattice parameter is given corresponding to second order diffraction maxima for X-rays of wavelength 0.71 angstrom units. The same thing. Same thing from Bragg's law. Let us solve this one. Solution. Given, what is given? Glancing angle on the cube. That means HKL is given. HKL is equal to the plane 1, 0, 0. Plane is given. Lattice parameter A is given. 2.814 angstrom minute is given. It is second order diffraction maxima. Second order means n is equal to 2. And X-rays wavelength is given, lambda is equal to 0.71 angstrom minute. Now what you have to find? Glancing angle. That means theta we have to find. What is the formula? 2d sin theta is equal to n lambda. Again, the interplanar spacing d is not given, but it is a cubic crystal. Solid crystal means for cubic crystal d is equal to a by square root of h square plus k square plus l square. Now this is d is equal to a means it is given 2.814 angstrom minutes by square root of h square. H means 1 square plus 0 square plus 0 square. That means obvious it is 1 square plus 0 square plus 0 square. It is again 2.814 angstrom minutes. That means d, we got the d value. Now what you have to find? Theta. So from this expression, sin theta is equal to how much? From this, sin theta is equal to n lambda by 2d. n lambda by 2d. That means theta is equal to sin inverse of n lambda by 2d. So this implies sin inverse n lambda means how much? 2 into lambda means how much? 0.71 angstrom minutes by 2 into d means how much? 2.814 angstrom minutes. 2.814 angstrom minutes. So angstrom minute will get cancelled. Now if you solve this one, theta is equal to, if you solve this one, you will get theta is equal to 14.61 degree. That is the glancing angle for this expression. So from Bragg's law, lambda is given, n is given, and d interplanar spacing we can obtain from the interplanar spacing expression. Then we can find theta value. Okay. Now let us go for next numerical. So let's say this monochromatic X-rays of wavelength 1.5 angstrom minute are incident on a crystal plane having interplanar spacing of 1.6 angstrom minutes. Find the highest order of which Bragg's reflection maximum can seen. That means what is the highest order? That means limitation of Bragg's condition is asking. Okay. Okay. Let us solve this. Solution. What is given? Lambda is equal to 1.5 angstrom minutes. Interplanar spacing means 1.6 angstrom minutes. What is the what we have to do? Find highest order. That means n maximum. What is the n maximum that we have to find? Okay. So according to Bragg's law, what is the formula? 2d sin theta is equal to n lambda. What is the limiting condition? That means n value should be maximum. When it will become maximum, this value is maximum. Maximum value of sin theta is 1. So 2d is equal to n max. That means n is maximum when sin theta is maximum value. Because d is fixed, lambda is fixed. So these are the constant values. So n value depends upon only angle theta. That also we have seen in the animation also. If we change theta angle, then the order of diffraction will change. So theta maximum value means sin theta is maximum is 1. So 2d is equal to n max lambda. So n max is equal to lambda by 2d. This is the formula. Now if you substitute this one, it means n max is equal to lambda means, what is the lambda? 1.5 angstrom minutes. 1.5 angstrom minutes by what is the 1.6 angstrom minutes. 1.6 angstrom minutes. Now if you solve this one, then you will get something like 2.3 something. That means we can say n is approximately, there is no fractions will be there, so it is a second order maximum is obtained. That is a maximum. Only 2 orders of diffraction only obtained for this lambda and for that interplanar spacing. Okay, so from this, in this lecture we described about Bragg condition, and that means Bragg's law. The Bragg's law means it is like a diffraction. Whenever diffraction will take place, then there is always the condition 2d sin theta is equal to n lambda is arrived. But what is the purpose of this Bragg's law? Purpose of this Bragg's law is, if we know about the Bragg's law, from this Bragg's law we can identify what is the interplanar spacing. Those things also we can identify. So that also we have seen, and limiting condition of Bragg's law also we have seen, lambda by 2d is less than or equal to 1. Okay, so now it's time for assignments. In the assignments, just I want to do one numerical. Just one numerical, one plane is given, FCC crystal structure is given, incident angle is given, that means grazing angle is given, wavelength is given. You have to calculate lattice parameter. Okay, so that you have to do as a assignment. So with this we conclude here about Bragg's law, and we'll meet in the tomorrow's lecture about X-ray diffraction techniques. Till then, thank you. Hello everyone, welcome to solid state physics course. Today we are going to discuss about X-ray diffraction techniques, especially Lawave method. This is the part of unit 2. Hello everyone, welcome to engineering physics course. Today we are going to discuss about Lawave's diffraction. Lawave's. Hello everyone, welcome to engineering physics course. Today we are going to discuss about X-ray diffraction techniques, especially Lawave's method. Okay. Let us discuss about Lawave's method. So before that, let us see what we discussed in previous lectures. Previously we discussed about Bragg's law and the 2d sin theta is equal to n lambda, the condition we arrived, and also limiting condition of Bragg's law also we have seen. And now what is the advantages of this X-ray diffraction techniques? Means, for example, a material is given to you, some metal is given to you, then you have to identify what is the crystal structure of this metal. That means you don't know what is this one. Okay, so we have to identify. How you have to identify what is the crystal structure of this one? In the unit 1 we discussed about, if you know the crystal structure, then mechanical, electrical and magnetic properties also you can correlate. So that it is important to know crystal system or crystal structure of the material. So for that the X-ray diffraction techniques are utilized. There are many techniques are there, among us we can classify X-ray diffraction techniques. Many techniques are there. We can classify X-ray diffraction techniques into two: Lawave method and powder diffraction methods. From the X-ray diffraction techniques, we can identify lattice structures, lattice parameters, crystal structures, and we can calculate interplanar spacing. There are so many advantages are there, or applications are there from these techniques. Okay, let us see what is the X-ray diffraction technique. That means we are taking some X-ray source. From the X-ray source, X-rays are incident on a sample. Then the rays, that means X-rays are getting scattered, as we discussed in Bragg's law. X-rays are getting scattered because of atomic planes are there, or atoms are there. In that atom, electrons are there. Electrons having negative charge and electromagnetic wave. X-ray means electromagnetic wave. Then there is electric field vector is interacting with the electron. Then there is a scattering is taking place. The scattered rays are coming. That detected. That means how many rays are coming, at what angle the rays are coming. The detector is detected. That from that we can identify the scattered ray, that means diffraction pattern we can identify. This is what X-ray diffraction technique. Let us see what Lave method is saying. The Lave method is saying that X-ray tube, from that X-ray you take a small hole. Okay, you take a small hole because we have to make it a beam is a fine beam. If the fine beam of X-ray is incident on a here, single crystals are used for the Lave. So first Lave is perform this experiment on single crystal, means it is only one single plane in a particular only one particular orientation of the planes are there, that is called single crystal. But the X-rays are having different wavelength, that means 0.2 to 2 angstrom, that means not a monochromatic source of X-ray. There are different lambdas are there. For different lambdas, if incident on it, then because of different lambdas are there, according to Bragg's law, 2D sin theta is equal to n lambda. If lambda is changing, theta is also changing. So different angles thetas are there, so that you will get a dots are present on the scene. This is photographic film. So there you can see the spots. So this is what Lave is observed. That means from this we can identify which type of material, because the what are the spots pattern are coming, that is not same for all the materials. If you keep iron, one type of pattern will come. If you keep another copper you take, then another pattern. Like our fingerprint. Our fingerprints not same for everyone. Like that, every material will have different type of pattern is called. This is called diffraction pattern. Different types of diffraction patterns are present for the different materials, so that from this we can identify what is the crystal structure of the given material. So how it look like? See, this is X-ray tube. From this X-ray tube, X-rays are incident on a material, that means single crystal is here. Now if you get the photographic film, it's like a cone, because it is diverse, scattered rays are in diverse and forms a cone. From this cone you will get, on photographic film you will get a image like this. Center is bright spot is there, small dots are present here. This is a diffraction pattern. So it is having the some particular fashion is there. Here one spot is there opposite to one spot, here one spot opposite to one spot, it is opposite to one spot. As I told you earlier also, these spots are not identical for all materials. One material will have different types of pattern, another material will have different types of pattern. So depends upon the material or what is the crystal structure, based on that the pattern is always changing. So from this we can easily identify what is the crystal structure of the given material. So it is one of the best example or application for the X-ray diffraction or Bragg's law. So from the Bragg's law we can identify what is the despacing and all. So what are the pattern that spots are coming, all because of the Bragg angle. So here, from here to here, so here from here to here, the distance we know about how much distance is there. For example, let's say distance is something like d, and now what is the pattern from the center, from here to here, this distance also we know. Since it is from this ray, that means from, if we imagine like this, then it forms a right angle triangle. Then what is the angle of this one? Basically this angle is what? Bragg angle. That means it is basically, this is 2 theta. This you know the distance d. This is d distance, that means from the sample to screen. Distance between sample to screen, that we can measure. And on the photographic film, what is the length from this here to here, that also we can measure. So from this, sin 2 theta is equal to x by d. X you know, d you know. So from this we can measure the theta. If we know about the theta, that means angle of incident angle, then from that we can identify from Bragg's law. If you know the theta, d and lambda you know. So from this we can identify what is the interplanar spacing and what is the crystal structure also we can identify. So partially, not completely, partially Lave method is useful to identify the crystal system, crystal structure of a given material. This is the best technique. The initial technique, the first technique Lave is introduced for X-ray diffraction. Okay. So this is the first and foremost technique of X-ray diffraction to determine the crystal structure of a given material. So from this we conclude this Lave method is that Lave method is basically is useful to understand or identification of crystal structure from that lattice parameter, interplanar spacing. Those values we can identify or we can determine from that values. So basically X-ray diffraction techniques are two methods are there, Lave method and powder diffraction method. In Lave method, single crystals are used. In powder diffraction method, there is a polycrystal, not a single crystal. That means the atomic planes are having different orientations are there in polycrystal method, polycrystalline materials. Okay, so this is about Lave method. So this is the end of the topic of this unit. So crystal planes we have discussed, and Miller indices we discussed, and interplanar spacing we discussed, Bragg's we discussed, and finally Lave method is discussed. So unit 2 of this course is completed. Okay. Thank you one and all. Thank you. Thank you for listening. Thank you. So this is the end of the unit 2. Unit 2 of this course is completed. Thank you for listening and thank you all. వల్లి గారు అయిపోయిందండి వచ్చేయండి. ఓకే.